and we'll start with the current slide. But before we get going on the current slide, there are a few announcements. First, of course, we're in the middle of Cougar Connection Week. We've been talking about it for a while. Today, Tuesday, on this campus, the title is Get on Board Volunteer Fair / Volunteer Fair. Where is this located? Outside the library. Now, the library's down on the main floor of this building, the ground floor of this building, and if you go down either of the next two exits, well, actually, go to the first exit here, go down one flight, go out of the building, and then when you do that, you'll probably start seeing tables along the side of the building, but if not, going around the corner, and there's a little courtyard that's sort of depressed between the A and B building. If you come in that back side at the Student Services entrance, it's down a set of steps from there. That courtyard is where I think all these tables will be set up, but they'll probably come around the side of the building as well. Here are some of the possible volunteer opportunities you have. I don't know if all of these groups are going to be here, but I bet you most of them will be. Big Brother, Big Sister, Big Green Housing Authority, they got mine so small I can hardly read it. Faith Chapel, Girls Incorporated, Grace House, Hands on Birmingham, Humane Society, Metro Changers, Oaks on Parkwood, Operation Hope, Powership Network, sorry I can't talk, and Red Cross. Now I've heard it said that they had tried to get a blood drive this week too, but they couldn't get it this week, so it's going to be next week. So Cougar Connections will continue next week as well for the blood drive. Then other student organizations that may have tables out there, hopefully they will, are groups like the Ambassadors, Athletics, Fine Arts, Honors College, PBL is Phi Beta Lambda, mostly a business type organization, but anyone can join it. Scholars Bowl, Student Government Association, Speech and Debate, Student Support Services, or Science, Technology, Engineering, and Math, the STEM program. Okay? They didn't include the math club or math team, the prime examples, but if you want more information on that, see me, see Miss Nyla Gerasi, who is the one of the math instructors on the Birmingham West campus. She's the coach of it. And they meet every Friday morning, 9:30 to 10:30. And Birmingham West campus, the C Hall, which is the science building, room 100, C100. Okay, if you happen to be on the Birmingham campus later today, from 12 to 1, the Constitution Day presentation will be in Thelma Catman Auditorium, which is it's in the library building, D Hall, but it's not at all visible, okay? It's off a little hallway through a couple doors, but it's real close. It's just you don't see it, you don't know it's there. Ask anyone in the library where Thelma Catman is. They'll point you in the right direction. Nice little auditorium there. That's from 12 to 1 today, the Constitution Day. Tomorrow, since we won't be meeting tomorrow for me to tell you this, on this campus will be an HIV awareness seminar, and that will be in the I cannot read this. It's it looks like 195, but I can't imagine where that is. Let me run out into the hall. They have a bigger poster there that's easier to read. A105. Okay? Let me think of where 105 would be. Is that the Space Center? Maybe that is the Space Center 105. Does anyone know? I think that's the Space Center. Okay. 105. Is that right? Yeah, I believe that is too. So that's where it will be tomorrow. HIV Awareness Seminar. It will be from 1 to 2 o'clock tomorrow afternoon. And on the Birmingham campus, they're having what they call Serve Day, and that will be at 3 o'clock in the afternoon. Okay? And then I'll go over the Thursday with you Thursday morning. This is so hard to read. All right. Now, there are a couple of other announcements. These I pulled off yesterday, and you probably have seen these if you've checked your email. If you've checked your email, okay? This is the time, I'm guessing that y'all are fairly well along your program of study, most of you anyway, but I don't know if any of you are quite ready to graduate. I doubt it. Are any of you close to graduation? You are. You are. Huh? This term or next term? This term. Have you applied yet? Not yet. There's a new online graduation application and a thing of doing it. I've seen a few of these posters up. This one should have printed this way, but it printed this way, so I didn't notice it until this morning. First, you do a degree audit, and I think you do that online, okay? You can check at the rector's office and find out, okay? Then, once you do your degree audit, you see your advisor, bringing with it everything you had, your degree plan and that type of thing. And then you apply online to graduate. You don't have to do a paper copy anymore, okay? And they, if you're graduating this term, this is the time to do it, okay? Even if you're graduating spring term, this is a good time to start the process. That way, before we even register for spring, you can know the courses you need to take in order to graduate on time. So it's a great idea to do it the term before you're graduating, but if you have it by the time now, this is a great time to do it. Now, here are some other opportunities that you may have. Now, it sounded like most of these are Birmingham campus, but I bet you we have the same things here, and even if you can head over to the Birmingham campus, they already have classes over there. What they need, the Office of Student Services, is seeking students who are interested in becoming note takers. I taught a guy, he was in a wheelchair, I'm guessing it was cerebral palsy. He couldn't write, so he couldn't take his own notes. So we provide someone to take notes for him. You get paid, okay? It's not a freebie. It's not just volunteer. You get paid by the college to be the note taker for that person. So I know there are some other folks that may be in similar situations. So if you would like to do that, consider doing it. You can contact Mrs. Janine Jones on the Birmingham West Campus, Student Service Specialist. She's in the Leon Kennedy building upstairs in their space center or somewhere close to it. If you want to contact someone here, Dr. Renee Herndon here can help you out as well. I think this must be a Birmingham need, so that's why they're advertising it. But if you can be over there, or if there's also a need that arises here, you can do it here. Now here's another, and this involves the Space Center. Now again, this is the one on the Birmingham campus, but I bet you the same thing is needed here. The Space Center is looking to hire peer tutors. That's you guys, okay? In areas of math, okay? English, biology, computer science, and Spanish. So if you are good in any of those. I know you're good in math. You're probably well beyond most of the people who are needing tutoring. So if you can, but you may be good in English, biology, computer science, and Spanish as well. So you can contact on the Birmingham campus Ms. Leslie Harper, or on this campus, I can't think of the gentleman's name, but he's just down in room 105, A105. Go down and check with him and see if he needs any tutors. And if you can go to Birmingham, you can be a tutor there as well. All right, good deal. Any questions on those? Sorry, that probably took longer than it should, but and I started marking the roll, but I didn't catch everybody. Walter, is here. Good. Okay. Gavin's not here yet. Dawson's here. Andrea's here. Josh is here. Jake is here. I didn't catch you when you came in. Allison's here. Chris, not here yet. And Jalen's here. Okay. Any questions on anything we've done up till now? Okay. I realize that I know I gave the test to the people who were here last time. Is anyone here who did not get the test last time? Okay. We finished 4.4, so that was the point for the first test. So today we're still in Chapter 4, Trigonometry, but now we're starting 4.5, Graphs of Sine and Cosine Functions. Okay? The next section will be the other trig functions and some other variations on the theme, and then we'll get into the rest. But now we're just going to focus on sine and cosine. So we'll sketch the objectives here to sketch the graphs of basic sine and cosine functions, and we'll play around and do some other things to them. We'll use amplitude and period to help sketch the graphs of sine and cosine functions when they have variations in them. We'll sketch translations of graphs of sines and cosine functions. And remember, we have several of those. We have vertical translations, horizontal translations, and we also have they have non-rigid transformations. Okay, shifts are rigid transformations, reflections are rigid transformations, but some of the others are non-rigid. So we'll even look at those. We'll use sine and cosine functions to model some real-life data. Okay, that will be fun. So let's start with the basic sine and cosine curves. All right. In this section, we'll study techniques for sketching the graphs of sine and cosine functions, and the graph of a sine function is also called a sine curve. Now, why the big deal about it? In physics, probably chemistry, certain aspects of biology, engineering, just about anything you can think of, one of the basic functions you'll run into is the process of simple harmonic motion. Okay? And some of these examples we'll see at the end. Everything in nature pretty much follows cycles. And cycles, if they repeat themselves, can often be modeled with sine and cosine curves or functions. Okay? So, let's start with the basics. This figure here, 436, the black portion of the graph represents one period of the function, or one cycle of the sine curve. You can call it any way you want to. That's not the only one. You could have started here and gone to there. You could have started here and gone to there. You could have started here and gone to there. You know, you could have done any one period would be that. We usually start at 0 and go one cycle that way. Okay? The gray portion of the graph indicates that basic sine curve repeats itself indefinitely forever and ever and ever and ever in both directions. Okay? Now, we call this a periodic function because it does repeat itself. It repeats this period over and over and over again in both directions. The period is 2 pi for the sine curve, the basic sine curve, y is equal to sine x, because that's when. Now, sure, there's a 0 here and there at pi, but this one's going up, that one's going down. That's not the same, okay? This one's going up, that's going up. Those are the same, so that's where the period begins again, okay? The range for a sine function, the basic sine function, y is equal to sine x, is always minus 1 to 1. Inclusive, the minus 1 is there, the plus 1 is there. It never exceeds, gets outside of that range. Okay? Any questions? Pretty straightforward. Just if you're wondering, this is point represents sine of 0, which is 0. This is sine of pi 6, which is 1/2. Pi quarters, which is root 2 over 2. Pi thirds, which is root 3 over 2. And pi halves, which is 1. And then they don't do them all coming down, they just do the 3/4 pi, then 3/2 pi. That's what some of those points are. The ones we're familiar with that we know and love so dearly. Okay. So there's your basic sine curve. Thing to keep in mind, sine starts at 0. 0, 0, goes up here, down here. Odd function, okay, whatever it's doing on this side, it does the opposite on this side. Okay, so it's going up there, going down here. But at the same values, just opposite direction. Period is 2 pi, it repeats that every time. Hang on to that concept because that's going to be really important later. Okay. The graph of the cosine curve looks almost just like the sine curve. It's just where it begins. Okay? It begins at 1. And we knew that already. Cosine of 0 is 1. And then it goes down to 0 to minus 1, up to 0 again, and then back to plus 1 again. Okay? That's one complete cycle from here to here. Or one period. 2 pi again. Okay? You could have started here to there, that would have been fine. Here to there, that would have been a cycle. You know, anything here to here would have been a cycle. Anything that covers 2 pi, a period of 2 pi, we usually define it to be 0 to 2 pi. Okay? Not always. There will be times when we'll do it with, we'll talk about that later. Okay. Again, the period is 2 pi, just like it was for sine. It's just different values in those 2 pi. The range is exactly the same, minus 1 to 1, just like it was for sine. Hey.
Sorry to disturb you. I was trying to go around, let all the instructors and students know to get on board day today starts at 11. We're serving hot dogs and hamburgers in the car at 11:30.
Oh, really?
Mm-hmm.
Okay.
Yes,
I thought it started at 8. Is that on the thing?
Did it say 8? And maybe on the other campus. Was this campus or the other campus?
Okay.
I don't know. But it's 11, I think, from 11 to 1, but we'll be ready to finish cooking coffee at 11:30.
Okay.
So we'll have food.
All right. That's out there by the library, right?
Yes, sir.
A little court. Thank you.
Mm-hmm.
I guess this is almost not really nice, but in the Navy we had the plan of the day. It was published every day, and you read the plan of the day, and the nickname for it was the Word. Did you hear what the Word said? Well, they every now and then they'd have the Word published in the morning, but then by afternoon it had changed. So what they would say, very irreligious, they say, in the beginning was the Word, and the Word was changed. So that's what happened here too, because on here it says, get on board Bessemer campus time 8 a.m. to 1 p.m. So evidently it's 11 to 1 now, or sometime therein. I wondered why they had anything at 8, because classes don't start till 8:30. I thought, there's not that many people here at 8. That's fine if you want to have it. So that may be why they changed a little bit. All right, so there's the cosine function. The thing to keep in mind, at 0 is 1. Sine is 0 at 0, and cosine is 1. Sine is increasing for the first quadrant, cosine is decreasing for the first quadrant. But guess what? Everything is in the first quadrant. Everything. Positive in the first quadrant. Cosine is decreasing there, sine is increasing there, but they're all positive in the first quadrant. You see there, sine is positive in the first quadrant, 0 to pi halves. Sine is also positive in the second quadrant. Cosine is not. It's negative in the second quadrant and third quadrant, but goes positive again in the fourth quadrant, just like we saw before. All students take calculus. Okay. Now, we know that the domain of the sine and the cosine function is set of all real numbers. There's no limitation anywhere. But the range is always between -1 and 1, inclusive, including -1 and 1. The period is 2 pi, okay? And you see how that's consistent here. Everything is just like we said before, nothing new here. I didn't point out our favorite functions here. This is cosine of 0 is 1, cosine of pi 6 is root 3 over 2, cosine of pi 4 is root 2 over 2, cosine of pi thirds is 1/2, and cosine of pi halves is 0. Okay? And you go down here, and for some reason they throw back in 3/4 pi, 3/4 pi. After that, it's every half pi. Okay. Now, most of the time in the future, when I'm graphing these, I'm going to put the ones I graph are the zeros, the maxes, and the mins. That's, if I got that, I can make up the rest of it. I don't usually do all the little points in the okay. Now, note that in both of those figures, the sine curve is symmetric with respect to what? Oops, this one. Sine curve is symmetric with respect to the, it goes with being an odd function. The reflection is across the origin. The cosine function is across the y-axis. That makes cosine an even function with odd, the sine an odd function. Okay. That's what they're asking you to note here. Those properties of symmetry follow from the fact that the sine function is odd, the cosine is even. Okay. Now, I don't know if you remember in pre-calculus algebra, we talked about even and odd functions, but in algebra, frankly, most functions are neither. I mean, just occasionally you'll have one that reflects across the origin, some across the y-axis. And those are nice special functions when they do, but most of them are neither. Your trig functions, unless you have a shift or something, they're almost always symmetric, either about the y-axis or the origin. So they're almost always well, they do follow some symmetry pattern, always. It may not be the y-axis of the thing, but because they're periodic, they're symmetric. They're symmetric about something. Okay. So, to sketch the basic graphs of the sine and the cosine functions by hand, it helps to note the 5 key points in one period. There are really only 4, but we counted 5 of each graph. And that's like I said, the intercepts, where it crosses the x-axis and y-axis, one place on y. Max points, min points. Okay? Now they call it 5. Technically it's only 4. But for the sine, let's see, 0, pi halves, pi, 3 halves pi, and 2 pi. An intercept here, here, and here. You see 2 pi is starting the next cycle. So that's really part of the next one. But it's good to go and get that done too. Pi halves is your max, and 3 halves pi is your min. And your pi's are your intercepts. For the sine. For the cosine, it starts at its maximum at 0, and then it's got a y-intercept at pi halves and 3 halves pi. It has a minimum at pi, and then goes back to its maximum at 2 pi. So, again, these two are the same point, but that's where they get the 5. 1, 2, 3, 4, 5. Those are the same points, just one period later. That's the beginning of the next period. But It's a good thing to do. In fact, I do as many periods as I'm going to do. I plot all of those. And you'll see when I do that. So that's your sine function. Now, again, think in terms of periods, the full period, and then these are your half and quarter periods. So once you know the periods, I always divide that by 4, because those are going to be my key points. Once you know what the period is, divide it by 4, those are going to be your key points. Intercept, max, intercept, min, intercept, or max, intercept, min, intercept, max. Whatever it is, those are going to be your key points. Your quarter periods. Okay. Hang on to that thought. All right, we're ready, I think, finally, for example 1. Okay. Sketch the graph of y is equal to 2 sine x on the interval from minus pi to 4 pi. Okay, let me get my pen set up. Okay. All right. Generally, I draw the horizontal axis wherever I want it, pretty much in the middle, because you know it's going to go up as much as it goes down. And since we are offset here, I'm going to put the y-axis something about like that. Okay? Now, they've already told us that needs to be minus pi. This, of course, is 0. So this is going to be, I don't have it done well, but that's okay. I can live without it. That's going to be pi. It's going to be 2 pi. This is pretty lousy, isn't it? Let me correct. Okay. All right. This time, I'll start in the middle. Okay. And do the endpoints. It's going to be minus pi and 4 pi. Okay? I think that might do it. Let's see. 1, 2, 3, 4, 5. Why am I having such trouble with this? All right. All right. I'm going to go with this, but I'm going to erase my notations here. All right. We'll put the origin here. Minus pi, pi, 2 pi, 3 pi, and 4 pi. Okay? And this will be minus 2 pi. They didn't ask us to do that, but I'm going to do it anyway. Okay? And this, of course, is 0. Okay, sketch the graph of y is equal to 2 sine x on the interval minus pi to 4 pi. Where does sine begin? 0. At the origin, it's 0. Okay? And where does it go? Okay. What is its period? Period for sine. It's 2 pi. And then you're going to have another at 4 pi. And you'll have one at minus 2 pi. So those are going to repeat themselves there. But in between every period, there is also another intercept that's going in the opposite direction. Okay? And in between each of those, we have our max and our min. So at the half pi's, we have our max and our min. Now, I didn't quite get these spaced well. Okay. Where does sine go from 0? Up or down? Up. And how far does it go? Normally. Plus 1. But this has a coefficient of 2, so that's now going to go to plus 2 and then also to minus 2. So it'll go, this is 1, 2. It goes, in this case, sine goes to 1. You multiply it by 2, it goes to 2. So down, and then you go to a min, a 0, a max, a 0, a min, a 0, and going backwards, a min, a 0, a max, and another 0. So here is the graph from minus pi to 2 pi. I just drew an extra half cycle in there. Now, about drawing your curves. They are curves, not straight lines. So there should not be any points. They should all be rounded on the maxes and the mins. Rounded, not pointed, okay? Because they are curves, okay? They should intersect your intercepts, which of course they do, and they should go the right directions after that. So in between every intercept, there's either a max or a min, and it starts off going to that. So there's the graph. If you start right here and go to 2 pi, that's what they were asking for. Because I had trouble drawing on space properly, I went on and did 6 divisions rather than 5. Just made it easier to do. All right, any questions? It's pretty straightforward, okay? Nothing deep. In fact, it should reinforce everything you ever knew about it, okay? That the sine of pi 6, which would be here, should be awfully close to 1/2 of the value here. Minus curving in too much, it should be around. Okay. But you get the general idea. Okay, so that was example 1. And by the way, LarsonPrecalculus.com, which you don't need any code for, it's an absolutely free website. Anyone can go there anytime they want to. They have an interactive version of this type of an example there. So if you'd like to see a little more, you can. Now, they also drew, when they drew their graph, they drew the basic sine curve. This was what they asked for, but they also drew, and someone give me a color. Pick a color, any color. Second? Purple, okay. All right. And we'll do y is equal to sine x with purple. It's just like this, it's 0, 0, but here it'll be a pi halves 1, then a 0, 0, then a minus 1 here, a 0, 0, a plus 1 here, a 0, 0, a minus 1 here, a 0, 0, a minus 1 here, a 0, 0, a plus 1 here, a 0, 0. So your basic sine curve is like this. And what they haven't told you, you just did a transformation. You did a non-rigid transformation. You multiplied by 2. So you stretched everything. Double stretch. Double 0, you stay 0. Double 1, you get 2. Double minus 1, you get minus 2. So you just doubled that. That's what the 2 in front of the sine x does for you. So y is equal to sine x is the basic purple curve, and then your actual graph was the dark curve, black curve. All right. There is a checkpoint at the bottom of the page. If you need more practice and want to do more, also at LarsonPrecalculus.com, audio, video solutions for that checkpoint. All right, that's how we did it. Let's see how they did it. They carry out and do a lot more brouhaha than I do, I think. But, okay. Now, how they start is note that y is equal to 2 sine x. That's exactly what they gave. Is exactly 2 times sine x, which I can't imagine it being anything else, okay? So if you plot the sine x, then double every value, and you get the 2 sine x. indicates the y values are for the key points will have twice the magnitude of those where y is equal to sine x. That's all you're changing is the magnitude. Later we'll call that the amplitude, and we'll talk about that as well. Divide the period, and this is what I said I do always. Divide the period, 2 pi, into 4 equal parts. So 2 pi divided by 4 is what? 2 pi divided by 4. 2 pi divided by 4. Pi halves? Exactly. Okay? And that will be, and that's what we chose as our point set. So sine starts at 0, 0. It goes up to its max. And because it's 2 times sine x, that goes up to 2 in this case. So pi halves 2. Then back to the 0 at pi. And then down to minus 2 at 3 halves pi. And back up to 0. Just where it started here, going in the same direction. Note it intercepted 2 pi. Because 2 times 0 is still 0. 2 times 1 is 2 times minus 1 is minus 2. Does that make sense? They like to draw these things out every time. I draw them on the graph. Okay? I don't see why write them and then draw them on the graph. By connecting those key points with a smooth curve, no points, no cusp, nothing like that, always a smooth, rounded curve, extending the curve in both directions of the interval from negative pi to 4 pi, you obtain this graph. See, I went on and did one more note here that you don't need to. Negative pi, 0, pi, 2 pi, 2 pi. All right, does that make sense? They did their sine curve in the gray and the 2 sine x in the darker curve. Any questions? All right. I've already mentioned the term, probably shouldn't have out of sequence, but amplitude and period. We've already been talking about period. What in the world do we mean by amplitude? Right. How far it goes off the equilibrium to its max and its min values. That is the amplitude. It's an absolute value. It's always positive. So the rest of this section will study the graphic effect of each of the 4 constants, A, B, C, and D, in equations of the form. And for the life of me, I don't know why they do it this way. I think I have maybe a little clue. But why in the world wouldn't they say y is equal to A sine of bx minus c plus d? That would give you A, B, C, and D. They put the plus d in front, which is perfectly fine. There's nothing wrong with it. I guess so you don't think that's part of the sign argument, that you know it's in front. So they do the d in front. Later we'll put it at the end too, and they'll do it. The other thing I don't like about the way they do it, I would factor out the b here, and then have my C be C over B. That's a lot cleaner. That in physics, that works a lot better. But they include it in the parentheses like that, which is fine. But when you do go to work with it, you factor out the B, and then you treat what's left over, C over B, as an important entity. C itself has not that much importance. And C over B, in this case, does have significant importance. We're going to focus on the A for right now. The constant A, factor A in both sine and cosine here, y is equal to A sine x and A cosine x. I'm showing that. That's just like in the last example, the 2. That's how far above or below the equilibrium line you went. Okay? That acts as a scaling factor, and that's exactly what it is. We scaled up, doubled everything in the last example. It's a vertical stretch, or if it was less than 1, it would be a vertical shrink. When the absolute value of A is greater than 1, the basic sine curve is stretched. When the absolute value of A is less than 1, the basic sine curve is shrunk. Vertically. They also have horizontal shrinking and stretching, but that's not what we're talking about here. Vertical. because you're multiplied by the function, the sign, the y value. Okay. As a result of this, the graph of y is equal to a sine x ranges now between minus a and a rather than minus 1 and 1. And the last example was from minus 2 to 2 because your constant was 2. The absolute value of a is called the amplitude of the function, the distance it rises or falls from the equilibrium position to the maximum endpoint. Y is equal to a sine x. The range of the function y is equal to a sine x for all a greater than 0, the positive a is from minus a to a. The reason I put that in there, if a was less than 0, then minus a would be positive and a would be negative, but so these would have to be reversed. So that's why we say for positive a's. Okay, the definition of amplitude for sine and cosine curves. The amplitude y is equal to a sine x and y is equal to a cosine x represents half the distance between the max and the min. Because I said from the equilibrium position to the max or equilibrium position to the min, so that would be half the distance between max and min. When we do the example later in the section, we will actually do this. We'll take the distance between max and min, have it, and that gives you your a. Okay. Absolute value of a. So the amplitude is always a positive number. A may not be positive. It may be negative. We'll talk about that later too, if it is. Okay. We will talk about it right now. The graph of y is equal to minus f of x is called the reflection in the x-axis of the graph of y is equal to f of x. Whatever was up here goes down there. Whatever was down here goes up there. When you negate it, it just moves across the x-axis. So it's reflection in the x-axis. So if we had a minus 3 cosine x, where does cosine normally begin? Cosine. At plus 1. If you have the 3 in front, that would be a plus 3. But if you do a minus 3 in front, it moves it down to a minus 3. Okay? And then it follows its regular pattern from there. But where it was going down, it's not going up. And where it was going up, it's not going down. So it just negates everything. Okay? So reflection of the graph, the gray graph here is y is equal to 3 cosine x. Reflect that across the x-axis. And you get minus 3 cosine x. You're negating everything. Okay. Does that make sense? The amplitude for both of those is 3. It's the absolute value of that a value. And it's half the difference between max and min, because it goes from plus 3 to minus 3. That's a total distance of 6. Half of that is 3. That's your amplitude. All right. Because y is equal to a sine x completes one cycle between 0 and 2 pi, it follows that y is equal to a, okay, they're throwing something new in now, introducing the b. What, multiply, okay. I don't know if you remember back in pre-calculus algebra, I don't know if your instructor said it this way, but I always say it in my class. The y's are always follow the rules exactly like you expect. If you add something to a y, it goes up. If you subtract something from y, it goes down. If you multiply something by y, it stretches. If you divide something or multiply a small number, the y by a small number is a shrink. Okay? X's do exactly the opposite in every case. If you have a x plus 2, that's going to the left. X minus 2 is shifted to the right. Any function of 2x, that's halving. If we do x over 2, that's doubling. I mean, the x's do everything backwards. Okay? So, and they're trying to explain it this way, and this is correct. But because y is equal to a sine x completes one cycle from 0 to 2 pi. One cycle, we know that. Sine is periodic at 2. But if you put a b in here, then bx goes from 0 to 2 pi, divide by b, and you get 0 divided by b and 2 pi divided by b. So basically, if b is a big number, you've just shrunk horizontally. If b is a small number, you've just expanded, stretched it horizontally. Okay? B is always counted to be a positive real number. So here's the period of sine and cosine functions. Let b be the positive real number. The period y is equal to a sine bx. A, absolute value of that is the amplitude. B affects the period. Amplitude, period. Okay? B affects the period. It's affecting the x. And the period is now 2 pi divided by b. So if b is increasing, that makes the period, if b is a big number, that makes the period smaller. If b is a small number, it makes the period bigger, meaning less than 1. Okay. So everything's backward with the x. Okay. Note that if b, remember we said b is always positive, so if b is between 0 and 1, the period y is equal a sine bx is greater than 2 pi, because that's a stretch, a horizontal stretch, and represents horizontal stretching. And on the other hand, if b is greater than 1, that's a horizontal shrink. So again, anything you're doing with the x's is always backwards. Okay, always backwards. Okay, I've got hiccup, sorry. So, and here's what I just said, put it on the next slide. When b is greater than 1, the period y is equal to a sine bx is less than 2 pi, represents a horizontal stretch. So for a smaller than 1b, it's a stretch, or greater than 1b, it's a shrink. Backwards, okay, but always that way. When b is negative, okay, then all you do is use your even and odd function. Sine being an odd function, that makes negative sine x. But if it's cosine negative x is the same as cosine x, because that's an even function. So just use that to rewrite it and then go from there. Don't haul around and do. Better to have the minus sign taken care of, if it's dealing with the x's. Fix it first and then deal with it. All right, so let's do this one. Okay? Now, I'm going to start you on the practice I think we need to be doing every time. I think when we have these variations like this, I wanted to do it last time, but I hadn't introduced it yet, so I didn't feel like I could. So now I will. First, identify what is your A. What's your A in this problem? Say again? Okay, yeah, it represents the amplitude, and what is it in that problem? 1, exactly. What's your B in this problem? Is what? It affects the period, but what is your B? The coefficient of x. No, 1/2. The B is 1/2. That's the coefficient of x. Okay. So the amplitude is the absolute value of A, so your amplitude is 1. Okay? Now, your period, what was the form that we dealt with the period? 2 pi over b. Now, that 2 pi is good for sines and cosines. And later we'll see it's good for secants and cosecants, okay, because they're reciprocals. It's 2 pi over b. And that would be, you're absolutely right, 4 pi. Because 2 pi divided by 1/2 is the same as 2 pi times 2, which is 4 pi. There's your period in this problem. The amplitude is still 1. Yes, and that's the next thing you do is divide the period by 4. And what would that be? The period divided by 4 would be pi. Okay. And that's key for what I'm going to do next. Okay. So we're going to sketch the graph. Your amplitude is 1, so we only need to go up 1 and down 1. Okay? I don't scale these things, what you might say, the same way every time. I scale them for that one particular problem. So don't let my 1 there make you think that the same distance on the x-axis is 1. It won't be, ever, okay? If it is ever, it's just blind luck. Okay, now we're going to use our quarter periods, 0, pi, 2 pi, 3 pi, 4 pi. That's one period, 4 pi. And we'll show negative pi, negative 2 pi, negative 3 pi, and negative 4 pi. That's another period in this direction. And you can do a negative 5 pi if you got room, and 5 pi out here if you got room, even 6 pi if you've got room, whatever. You know, you can draw as many as you want. But we're going to do them by our quarter periods. Okay? Where does sine begin? 0. And in the first quarter period, it goes where? Up to its amplitude, and its amplitude is 1. So it goes up to plus 1, then down to 0, down to minus 1, up to 0, up to plus 1, down to 0. Going in the opposite way, it goes down to minus 1, minus the amplitude, up to 0, up to the amplitude, down to 0, down to the amplitude, negative amplitude. So here's what your sine function looks like, this sine function. Now, if you were to superimpose that on y is equal to sine x, not sine x over 2, you want to do that or not? Just to see what the change is. Let's do it this time. What color you want the regular sine function to be? Give me a color. Red? Okay. Let's see if I can get red to the right. Yes, we did. Okay. The regular sine function, y is equal to sine x, it has a period of 2 pi. So that means its quarter periods are going to be the pi halves. So it goes up to 1 there, down to 0, down to minus 1, and up to 0. So, and it does that every time around. Okay, or I could go backward and do the same thing, but you see this is the sine function. If I could draw, it would be wonderful. Okay, so you see what the blue or the dark bit was stretched because your b was less than 1. A horizontal stretch. The vertical didn't change at all, not a bit. The horizontal was a stretch because you divided by 2. You multiplied by a smaller number, 1/2, and that made the period twice the size, 4 pi. So that would be your regular sine curve, the red. This is the vertical, horizontal stretch, and that's your blue curve, dark curve. All right. Any questions on that? I just realized we skipped example 2, didn't we? Sorry about that. Let's back up. Okay, we'll do example 2 here where example 3 just was. So let me get my pen back. All right. On the same coordinate plane, sketch the graph of each function. The first of these is y is equal to 1/2 cosine x. Okay? Now, before we do that, let's do the basic function. What color you want it? Y is equal to cosine x. What color you want it? You said gray?
Green.
Green. Okay. Light or dark? Dark. Okay. So let's do y is equal to cosine x first. Then we'll do 1/2 cosine x. And then we'll do 3 cosine x. But we'll do them on the same graph. Alright. Let me go back to my dark color and draw my graphs in here. Okay. And let's also identify what their parameters are. What does the 1/2 represent? Anybody? What does 1/2 represent? Okay, that is your amplitude because it's positive. So your A is equal to 1/2, and the absolute value of that would be your amplitude. So your amplitude is also 1/2. Okay? And what's your B? B is 1, so your period is going to be 2 pi. Okay. And then once you know the period is 2 pi, what do we do with that? Divide by 4. So the period is 2 pi, and period divided by 4 is equal to pi over 2. Pi over 2. All right. So that's going to be the increments I use. So here we're only going up to 1/2 and down to -1/2. Okay? And where does cosine normally begin? At its max, and in this case the amplitude is 1/2, so it's going to start there. Let's do our quarter pies out here. So quarter periods, so that would be 1 period, 1/2 a period, and these will be my quarter periods. So this will be pi halves, pi, 3/2 pi. Goodness gracious, I say 3/2 pi and write 3/3 pi. Something's wrong with this picture. And 1, which is 4/2 pi. I say 1. 2 pi. Goodness gracious, which is 4/2 pi. All right. And we could do the same thing in the negative direction and have this as minus pi halves, minus pi, minus 2 pi. I'm just going to write a few of them in there. Okay? Goodness, my eyes are dry. The cosine starts at its max, which is 1/2. It goes down to its 0, it goes down to its min, up to its 0, and up to thing. That's why I draw the quarter pies. They always follow that pattern. Okay? Going in the opposite direction, it's going down to a 0, down to a min, up to a 0, and up to a max. So this is your, whoa! Yeah. This is the function we have there. I didn't do the green function. Let's do the green function. It's going to +1 and -1. Now, I didn't leave enough room for it. So it's starting here and going down, going here, going up. And same thing here, down, down, up, up. Okay. So that's what your parent function was doing, the cosine function. This is a vertical shrink because you multiplied by 1/2, the function by 1/2, vertical shrink. All right, we're also supposed to do, I'll need a different color, so give me another color, folks. Any color. Yellow. Okay, that may be hard for you to see, but let's see if you can follow it. That's going to be y is equal to 3. Ooh, I wasn't looking ahead, was it? Y is equal to 3 cosine x. I should have planned ahead. I couldn't get 1 on the bottom down there, and I sure can't get 3 on either the top or the bottom. But that would be, if that's 1, 2 would be somewhere in 3. So that's going to be a real big vertical stretch from here. Sorry about it. I wasn't paying attention to my problem. So I think what I have to do is go back and redraw. But I'll only redraw the yellow part. So I'll erase all this ink and basically draw the same thing I had, except I'm going to change the scale of my and it's still, this is y is equal to 3 cosine x. Can y'all read that okay, or do you want me to go back to darker? Huh? You want me to change color? What do you want me to change to? Orange. Aren't you glad I changed to orange? I can't get it to change to orange. There we go. Is that somewhat better? Okay. So y is equal to 3 cosine x. Okay? So now my vertical scale, I'll do 3. This is minus 3, minus 1, and minus 2. 1, 2, 3. Okay. Your period didn't change any, so this is pi halves, pi, 3 halves pi, and 2 pi. Minus pi, halves, minus pi, minus 2 pi. Okay? Now, cosine starts the max at 0, goes down to 0 here, the min here, 0 here, back to the max here. Not a very pretty picture, but okay, basically that. And if we had the others in there, I'll do them just really quickly. The green was our sine. Whoops, I dipped too low. Okay. And then the dark was our cosine. Said that totally wrong. We go back to my green. The green is y is equal to cosine x, and my dark is going to be y is equal to cosine, not sine. Goodness gracious. Okay, that goes from -1/2 to -1/2. So it goes just this kind of motion. So to get them all on the same graph. Okay, I went a little too high there. So that's a vertical shrink from the green. This is a vertical stretch from the green. Okay. Kind of botched that all over the place. They like to list those individual points. Shoot, if you just get them plotted there, they fall into place right where they belong. There is a checkpoint bottom of page 299 for example 2, and then another one at the bottom of 300 for example 3. And we've already done that, so we have finished that one. Now, did we show how they did number 3? I don't think that I did. So let me erase this, and let's see how they did it. The amplitude is 1. We noted that as well. Because b is 1/2, the period is 2 pi over 1/2, which comes out being 4 pi, which you all picked up right up on. Okay? Okay. Sorry. Now divide the period. We already determined the period to be 4 pi in 4 equal pieces, so that would be pi, 2 pi, 3 pi, 4 pi, with 0 being the first one. Okay? Then do your intercept to each of those. Do your values of there. Because this is the sine function, remember. Sine of 0 is 0. Sine of the first quarter period is 1. Second quarter period is going to be a 0. Third quarter period is going to be a -1. And the fourth quarter period is back at the 0 again. Okay? Frankly, when I do these, I just plot those quarter periods on the graph paper or wherever I'm doing it. And then intercept max, intercept min, intercept. They just plot, and I don't see any reason to have to write them down like this. But if that helps you see it, do it, by all means. Okay, and there's the graph. And this one, they did the sine in the regular 2 pi period. That's the gray graph, and then the dark graph is your sine, except for 2. B is a smaller number, so therefore you have a horizontal stretch. Everything backwards in the horizontal axis. All right. Now we're going to translate the sine and cosine curves. And there's 2 ways that we can translate. One is horizontally, and the other is vertically. We're going to deal with horizontal first, and guess what? That's going to be our C. Okay? And again, because C is literally dealing with the x, your sign is opposite. So if you want it to translate to the right, it's going to be a -C. And here's what I don't like about this, the way they do it. The C is not the amount of translation. It's C over B is the amount of translation. So why in the world do they call it C? Well, they pull the B on the outside. That would be your amplitude. Your affecting your period, just like it normally would be, just like it does here. And what's inside then have what I call my C is their C over B. That is actually your horizontal shift. And you have to divide by it. And it just makes it sort of all doable, it's all correct, but it just makes more sense if you kept the B as the coefficient of the x and then do x minus C here. That would be your horizontal shift. The C would be a horizontal shift if that was in parentheses. When it's done like this, you have to pull the B out, and C over B is your horizontal shift. Now, they do it this way, and it works out exactly the way I'm saying. But this is such an awkward way to do it, okay? But it does work. Your C over B is your horizontal shift, and your 2 pi over B is your period. Just like before. That didn't change. So the number C over B is called the phase shift. Whereas when you're dealing with physics and circuitry and things like this, you pull the omega, which we'll call omega, the B out, and then the phase shift will be the constant that's left with the x. They just have the fractional form. Okay. So the graphs of this, A sine B x minus C, and y is equal to A cosine B x minus C, have the following characteristics. Assume that B is positive here. The amplitude is still the absolute value of A. The period is still 2 pi over B. And that would still be true if you pull the B out of the parentheses, which it should be. Okay? Then the left and right endpoints of one cycle would be these endpoints, which is fine, but you have to do manipulations. Add B to both sides, add C to both sides, and divide by B. So you actually start at minus at C over B, and this one would be 2 pi plus C over B. So it's just an awkward way of doing it. So let's sketch the curve of this graph. Now, have we skipped one here? Yeah, they skipped example 4. So before we do 5, let's do 4. Okay? Analyze the graph of y is equal to 1/2 sine of x minus pi thirds. Now this works out pretty nicely. Not that it doesn't have some rough spots, but let's deal with it. Okay, first thing I like to do is identify your parameters. What's your A? 1/2, and that is also your amplitude, okay, because it's positive. What's your B? 1, and that means that your period is what? Second? 2 pi. 2 pi over 1, which is just 2 pi. And in this one, your phase shift and, okay, because the B is 1, you don't have to worry with it, is actually pi thirds. Okay, let's go back to the period though, and what do we do with the period? Divide it by 4, and that would be pi halves then, just like normal. Here we have a problem though, Houston. We have a shift of pi thirds and a quarter period of pi halves. They're not the same things. So you have to come up with the least common denominator. And what's the least common denominator? 6. So I'm going to draw things in terms of pi 6, and then we'll go back and fill in. So that's what you do when your phase shift and your period don't match the denominators. Go with the least common denominator. So let's do it. And this is a sine function, so we know where it's heading here. All right. So I'm going to do pi 6. And I want this to be a 2 pi out here, and this to be a pi here, and this to be a pi halves here, and then let me stop and think a moment. Yeah, split this into thirds. This will be a pi 6, okay? And this will be, those will be 6th of pi's. Wait. This will be 3 halves pi. Okay. Going this way, we'll have our 2 pi out here, minus 2 pi out here, minus pi here, minus pi halves here, and minus 3 halves pi here. And then we'll do minus pi 6. All right. In gory detail, that's what we're doing. Okay? Now, keep in mind your quarter period is pi halves. Okay? That's going to be 3/6 of a pi. Okay? We've scaled everything in pi 6 here. Okay? Now, our phase shift is pi thirds, and it's to the right. The minus sign, because it's dealing with the x, is to the right. So we're going to start at pi thirds. Well, that's 2 pi 6, right? So we're starting right there. There's our starting point. Sine begins there at 0. I lost track of time. Yeah. And this is time to stop, isn't it? Oh, yeah. We'll begin next time with example 4. Sorry, we went through all that, not to have time to finish it. So, let me mark my place here. Whoops, let me also erase some here. Okay. Let's see, homework exercises here. I know you can do some of the odds 5 through 11. They're all at Calc Chat, 7's at Calc View. I think you can do any of the odds 13 to 19. No, maybe not all those. Let's say 13, 15, and stop there. Okay, they're at Calc Chat also. And we'll pick up the rest of these when we do the rest of the time. Good deal. We'll see you Thursday. And if you have questions on the test, bring them in. Okay. Anyone need the test? Everybody got it, right? Good deal.